Today, I'll tell you more about some of the work that we have been doing at the intersection of deep learning and optics, and how we can use some of these ideas for computational microscopy and diffractive imaging. So my lab in general is interested in computational imaging and sensing systems. Some of the earlier work from my lab involved creating mobile phone-based microscopy solutions, sensors of various different kinds. The idea there was to create inexpensive, field-portable instrumentation for microscopy or for sensing that would match the quality, resolution, sensitivity, specificity of their counterparts that you expect in lab-grade instrumentation, democratizing advanced measurement tools. That was what I've done for perhaps at least the first 10, 15 years of my lab at UCLA. Over the last about 7, 8 years, we have been more and more interested in the intersection of deep learning and optics and improving microscopy solutions. So here, we're more interested in image reconstruction and image enhancement using neural networks, not classification, not looking for margins of, for example, certain features. How to reconstruct images and how to enhance microscopes and how to utilize deep learning ideas. So we have a paper in 2017, which is now also issued as a patent, which essentially used deep learning for the first time for enhancing optical microscopy resolution and depth of field of optical microscopy. Over the last several years, we like using networks, neural networks, for image reconstruction or image enhancement tasks. The main reason why I like this framework is because of their non-iterative and fast inference. Traditional image reconstruction methods have been traditionally iterative, guess and correct, guess and correct. And through supervised learning, that has changed. And we can now use supervised learning to take, for example, bright field microscopy images that have diffraction limited resolution and improve them beyond the numerical aperture of your system, improving resolution and depth of field by learning a transformation between a low resolution system and a high resolution system. Sometimes these kinds of transformations through supervised learning also helped us to take, for example, an inexpensive handheld smartphone-based microscope and correct for its color aberrations and resolution limitations by training a neural network using several samples, tens of hundreds of samples against a diffraction microscope so that you can actually improve the performance of inexpensive microscopy tools. And we can also use it for coherent imaging, holography, and other applications. This was kind of like the first baseline stepping stone of using deep learning for enhancing image reconstruction and microscopy. One thing common in all of these examples is that the inverse imaging problem that we were solving here through supervised learning was known. So we knew what physically we were after. And oftentimes, a physical reconstruction model was our ground truth. And we were training a function approximator, universal function approximator, to come close to physics. And here, arguably, we were cheating and trying to be as good as a physical system because the physical forward model was known precisely in every one of these examples. Soon after this, we realized a bigger opportunity for enhancing microscopy, and that is approximating unknown functions. Approximating solutions where the physical forward model is not possible to establish. Even imagine a case where we cannot consider the physical forward model or its existence, its uniqueness. Now, through supervised learning, we can approximate functions that we don't have physical proxies for. And this, in my opinion, perhaps is arguably the most important application of deep learning for opening up new avenues for us in microscopy, optical microscopy. So this function F is peculiar and it doesn't give you a good idea at this point, I realize. Let me give you a little more idea. about what that F function could be, the unknown function that we do not know, the unknown unknown. Think of a function like this, where you take fluorescence microscopic images of samples, and you want to transform them into another modality, bright field. And that's a very difficult transformation. We don't have a physical forward model to link fluorescence to bright field. There are different contrast mechanisms. As if that is not enough of a transformation, I want the sample to be label-free, which means I'm looking at autofluorescence, no exogenous fluorophores. And at the bright field output, I want it to look like a labeled specimen. So not only the modality is transforming, but the sample is changing. So that's essentially a crazy difficult to model physical forward process, if there is ever one. Through supervised learning, we can attempt at these kinds of function approximations. You may be asking, hey, who cares? So what? I don't care about that F function, you may say. Well, perhaps I can convince you that the F function that I just described to you is extremely important, especially for pathology. So for the last 150 years, every time we take a biopsy out of a patient, it goes through this laborious chemical staining process, because thin sections of tissue under bright field, they don't have contrast. That's not sufficient contrast for diagnostician to diagnose the condition of the patient. That's the reason why we have invented various different kinds of fluorophores, chromophores, to dye the sample so that under a microscope, bright field microscope, it looks like this, revealing subcellular features. This is called histological staining process, chemical process, a very tedious, expensive process depending on the tissue stain combination. That F function that I just described to you, the label-free autofluorescence to bright field conversion, that could replace this whole histochemical staining process in pathology with a deep neural network by transforming autofluorescence images of label-free native tissue into bright field equivalents of the stained version, so that you do transformation across modalities and label-free to labeled. There's no external fluorescence here. So this autofluorescence signature is native. Every one of us have those fluorophores inside our body. Those are endogenous fluorescence coming from a soup of molecules at the subcellular feature. And a lot of times it's actually a headache for microscopists. Autofluorescence is a headache. Here, somebody's garbage is somebody else's treasure. So here, to do this cross-modality transformation for virtual staining, we call this virtual tissue staining, we're using a framework that is game theoretic in its core, which means it's based on a fight between a generator, a convolutional neural net, and a discriminator network. These are trying to fight with each other. It's called GAN, Generated Adversary Network Framework. It's not a traditional GAN that is famous for hallucinations, imagination. No, this is actually conditioned. The rule of the game for virtual staining of tissue, especially human tissue, is not to hallucinate, because nobody wants to pay a dime to diagnose patients that never existed. That's why we condition this generator with structural loss terms so that it's faithful to the input structure. Do not confuse these kinds of frameworks with noise input, hallucination output. This is a beautiful diffraction limited image with 200, 300 nanometer beautiful pixel size at the input, revealing all these nanoscale features of the sample input. That's conditioning the generator to be faithful to the micro and nanostructure of the tissue. The task of the discriminator is to bring another loss function to help the learning. And at the end of this game theory fight, nobody wins. Generator can fool the discriminator 50% of the time approximately, which means at that point you have a beautiful generator that is your virtual stainer. All those technicians in the lab who do staining of tissue, now they will be replaced with this generator doing it chemistry-free based on autofluorescence of tissue. Training takes time. There's a lot of details of image registration and training, scheduling of the learning rate to make the generator work. But that's a one-time effort. From scratch, it can take you a couple of weeks to get a good generator. But then it's done. And you can test it with infinitely many inputs of new patients. Everything that I'll show you in the next several slides, these are new patients never seen before. We're showing you generalization of the networks for new samples never used during, new patient samples never used during the training phase. For example, this one is H&E. More than 90% of all the stains in the world are using H&E stain. This is what comes out of a histology lab. This is my ground truth. A typical time for one of these images is about 2 hours. His technologies would spend 2 hours to create one of those stains. We use only autofluorescence coming from a standard filter. This is DAPI filter, but there's no exogenous fluorophore here. It's just a filter. It's contrast enhanced for your eye. What goes into the network is these images where you have just grayscale, and you have beautiful match with respect to the ground truth. These are the stoichemical ground truth, and these are the virtually stained counterparts. This is salivary gland H&E blind testing. It also works for more exotic special stains. For example, this one is kidney tissue, Jones-Silver stain. That's virtually stained from autofluorescence signatures. Jones-Silver stain typically takes about 3 hours for a technologist human to stain. And it's tedious. And that's why it costs approximately 10 times more per patient sample than H&E. These are more exotic stains. This framework works for various different tissue stain combinations. Some other blind testing examples are shown here. This is lung tissue sample, liver, and this is another type of stain, Mason's trichome. It's also about 3 hours for a technologist to stain it. Beautiful inference in just a matter of seconds from these autofluorescence images of native tissue. Only contrast enhanced for your eye as shown here. So these were stains where it's not molecularly specific. These are rapid stains using chromophores. This framework can also be used for more tedious and more expensive stains where we do immunohistochemical staining based on antibody-antigen interactions. This is kind of interesting and a very challenging task. An immunohistochemical stain typically takes 24 hours to stain, because your chromophore or fluorophore conjugated with an antibody needs to find the antigen expressed on the cell membrane, for example, and it takes a 24-hour cycle. This is probably the most expensive type of stain used in histology. We're sharing here an example of HER2 stain. HER2 is a breast cancer biomarker. If you're tested positive, the therapy can be determined based on the expression level of HER2. Some patients have overexpression of HER2. These are, for example, patient specimen in which the brown color shows you the overexpression of HER2. This is HER2 3+, and that patient must be treated differently than HER2 0. For example, these are HER2 0 samples, and that's very important to determine. Autofluorescence signatures at the nanoscale can tell us where these antibodies are binding statistically so that we can actually replicate even a difficult stain like IHC, immunohistochemical staining, and replicate these IHC stains that come after 24 hours in just a matter of seconds using autofluorescence also. Because it's a more challenging task, we are using several channels of autofluorescence here. But again, no exogenous fluorophore. Everything is endogenous. You just change the filter from DAPI to FITC, etc. These are some warm-up images of how to compare what comes out of histology versus what comes out of our inference models. But for a pathologist, these kinds of comparisons mean nothing. We gave them in a blinded manner for them to look at the quality of these stains. We created lots of these tables where the pathologist, a group of pathologists, was looking at our images versus what comes out of histology in a blinded manner without knowing which one is which. We asked them, hey, tell us the quality of the stain, like nuclear detail, cytoplasmic detail, extracellular fibrosis. What these numbers tell you that statistically, there's no difference from the quality perspective of the diagnosticians between our images and what comes out of traditional clinical workflow. In fact, we also gave them our images for them to diagnose the condition of the patient without, again, knowing if it's virtually stained or it's the chemical stain. Same decision, same outcome. There's clinically no significant difference in the diagnosis that they achieve with our technology versus the clinical workflow. That shows you that we are not just showing believable images, we're showing actually the micro and nanostructure that corresponds to the pathology of the patient. But virtual staining is not just about making things faster and chemistry-free. It has a ton of very important advantages. Arguably, one of the most important advantages of virtual staining is standardization of staining. So if you go to, for example, a very basic stain, H&E, more than 90% of all the stains are H&E, right? Look at, for example, UCLA Health, H&E samples. From run to run, you see quite a bit of variation. If you're an AI pathology company looking at, let's say, tumor detection, cancer detection, you will be overfitting to some of these styles, and it's going to be detrimental because your model might work in Southern California, but it has no chance of working in Europe. Virtual staining is standardizing staining quality. From run to run, you don't have variations. It's very, very important for diagnosticians, but it's also important for downstream neural network-based analysis of these images. And in my opinion, the biggest advantage of virtual staining is multiplexing. If you stain a tissue sample with one of these stains, you're done. You've depleted tissue. Oftentimes, multiple stains are required for precise diagnosis. If you have ever given a biopsy and the patient was called back again to get a secondary biopsy, you know what's happening? They're messing with your sample and staining with different stains. It's like a potato. They cut, stain, they cut, stain. And after a while, we bring the patient back again. All of that is unnecessary, so you can actually, from a single cross-section, virtually create a panel of stains chemistry-free. Rapid, consistent, and multiplex, without the need for ever calling the patient back again, because we do not deplete the tissue. Tissue can be used for other things. And for the first time, all of these stains are nanoscopically registered to each other, which means I can also do stain-to-stain transformations. I can take one of these stains and transform it into another one and learn transformations of any kind. That's actually a big power. This framework also works for cases where there is some tissue damage, especially for autopsy samples. Because of the delay in fixation, oftentimes the tissue is damaged through autolysis. Basically, proteins are going bad, especially if autopsy samples are processed late. And because of the large specimen area, this is unavoidable. We've shown that you can actually use virtual staining to get over staining artifacts that would normally hamper the investigation, because all of these are traditional autopsy samples stained with H&E. You see quite a bit of failure of staining because there's no binding because of the damage to tissue. We can bring them all back through autofluorescence signatures and show you that it also works for damaged tissue, because autofluorescence texture across different fluorescence channels is very resilient to some of these perturbations. So these were examples of one label-free contrast mechanism, and that was autofluorescence. That's my favorite contrast mechanism for virtual staining of tissue. But that's not the only label-free contrast. You can actually use other types of contrast of label-free tissue to do virtual staining. My second favorite is holography. So you can also use QPI, quantitative phase imaging. I'm sure holography is also Dimitri's favorite tools. So you can also use label-free QPI and holography and the optical path length information of the specimen as a label-free contrast to do another peculiar transformation. This transformation is more peculiar and more difficult to understand from the perspective of light-matter interaction, because this is spatially coherent, temporally coherent as well, and this is incoherent spatially and temporally. It's a very crazy transformation. And of course, label-free to labeled. So that F function could have never been approximated from the perspective of light-matter interaction and physical understanding of tissue. Through supervised learning, if I know the ground truth and beautiful registration of thousands of patches of these label-free samples, you can take optical path length information at a single wavelength to be transformed into bright field equivalent of the stained version of the same sample. Single frequency to bright field, spatially coherent to bright field incoherent. We call it phase stain, self-explanatory. We're using phase signatures, optical path length information of the sample. These are some blind testing results from skin tissue samples, beautiful contrast. Interestingly, this is the phase signature optical path length. Remember, tissue sections are thin, 3-4 microns. That's why you don't even use 2 pi range there. This contrast is sufficient for us to create virtual staining, nicely matching what comes out of histology without chemistry, using another label-free contrast mechanism. Some other examples of QPI to bright field transformation for kidney tissue, liver, 2 different types of stains. Again, these are more expensive, tedious stains that are typically performed in about 3 hours. Another contrast mechanism for virtual staining that we tried is reflectance confocal microscopy, RCM, but this is different than the others. This is biopsy-free. RCM is actually an FDA-cleared technology for dermatopathology. This device that you see here is a reflectance confocal microscope, FDA-cleared for use in dermatology clinics. Basically, without any labels, without any exogenous contrast, it images within 100 microns into the tissue and gives you sections in reflectance confocal contrast. Grayscale. And most diagnosticians don't like it because nobody is trained with grayscale. Everybody wants to see H&E contrast. In this work, we used virtual staining to take reflectance confocal stack of images and convert them into H&E equivalent images, but that one is biopsy-free and it's operating in vivo. So it gives you a stack of images that are translated into H&E-like contrast. This is actually a slide where I show 2 movies which tell you the stability of this inference process from device to device. This model was trained with this benchtop device. This is a RCM from a colleague of us, a pathologist, dermatopathologist. So this is a patient sample non-invasively by touching on the skin. We're imaging deep into the tissue and in real time showing you H&E equivalent images label-free. This is the scale bar, and here you're scanning into the skin. This is like starting from 0 microns up to about 0.1 millimeter with a few microns of Z-scaling. Now, everything here is blind testing. This patient was not in our training set, but this device was, of course, part of our training set. So this model only saw this device's data. If you take this exact model and translate it into another handheld version of the device, which is also a reflectance confocal microscope, but a completely different optics for handheld use, it actually works very well. So this is showing you external generalization to another device with the same contrast mechanism, but never used in our training. What makes this portability from one device to the next one for in vivo virtual staining is depth sectioning. What goes into the neural network is not just a single cross section. It's actually a sequence of images that makes it more resilient because we see an image cube that is actually used for inference of any one of these planes within the tissue. This is actually quite a surprise to me because usually neural network models trained on a device should have some transfer learning component when you change the device from Leica to Olympus, etc. This one is actually from one device to the next, first time plug and play ready. So this is what I showed you a couple of minutes ago. We can have perfectly registered images that are showing you the same tissue cross section with different stains. Using this, we can actually also do stain to stain transformations. This is something very interesting because if the stain is already done, let's look at, for example, hospitals around the world. You will find millions of images that are already H&E stained. Now, with these virtual staining networks, you can create image-to-image or stain-to-stain transformation networks that can take H&E and tell you how it would be looking under a different stain. That would be wonderful for analysis of existing tissue samples. And that's why we have applied this to stain-to-stain transformation to show that if the stain is already done, let's say H&E, we can virtually create these stain-to-stain transformation networks because virtual staining is the anchor point. From label-free contrast, I can go to stain A, stain B, stain C, and I can then hop from one to the next one to the next one because they are nanoscopically registered. Normally, if you want to do this, chemically, you cannot. Every time you take another section with another stain, they're different. There's no ground truth. So virtual staining is the enabler here for the stain-to-stain transformation. Who cares about these? Well, it speeds up diagnosis. So this way, we've shown that compared to H&E only, diagnosticians can diagnose the patient faster and more accurately if they could have these special stains virtually created. This will be very important for emergency situations. Let's say the patient comes with organ transplant rejection type of symptoms. Hey, I must act very quickly. It usually starts with H&E. These are longer and more expensive. Insurance doesn't pay immediately. So that means immediately as H&E rapidly is available, diagnostician can use these virtual stains if virtual staining of H&E is not possible. To sum up, virtual staining of tissue is a framework that saves time, chemical reagents. It's also a green technology. Millions of gallons of water every year is wasted because of toxic compounds used in staining of tissue. Because this is based on label-free imaging, it's also eliminating toxic waste. And you can do multiplexing, and you can preserve tissue. It means no need for secondary biopsies, etc. It's faster, consistent, and cheaper, and at the same time multiplex. This is not just working in my lab. We have commercialized this technology. So we have, in 2019, I established Pictor Labs as a spin-off from my lab. Pictor in Latin means, anyone wants to take a guess? Pictor in Latin means painter. So Pictor is a painter at the microscale. It paints microstructure of tissue. In 2019, we spun up the company. My COVID days were pitching this to VCs, and I started my pitches always with the same word. Pictor means in Latin painter. So we raised about $19 million to commercialize this technology, and the difference between us and traditional pathology is like the difference between Blockbuster and Netflix. If you want to, in today's pathology workflow, if you want to see a tissue sample on a glass slide, you take it physically, put under a microscope, inspect it. Very much like how we used to watch movies from Blockbuster, taking the DVD, etc. Netflix changed the game. So Pictor's technology is going to enable the diagnostician to, on demand, look at various different stains and create essentially diagnostic value. We are moving forward fast. We're about 25 people at Pictor Labs and currently trying to raise Series A by the end of the year. So this was the success of supervised learning, helping us approximate functions that otherwise was difficult to understand or even see if they exist. Everything is great on this perspective for supervised learning. However, supervised learning is also quite expensive. To get these things up and running, you need domain expertise. You need high quality data. You need image registration. You need pathologists to be involved during the training phase to do quality assurance. A lot of things I can tell you about failures in pathology you don't want to know, because if you know what I know, you probably would not want to give your next biopsy. So many things are random. Yes, so we got to have high quality, diverse training samples, most likely with pathologists involved. And also, the model is opaque. That function is unknown. Well, that's why it's opaque. Double-edged sword. And you might be worried about potential hallucinations. Pathology is a very conservative field. Hallucinations are not good. So you got to be very careful. Ask me a question about hallucinations. I can tell you 30 minutes of what I talk about to VCs, because that's also a concern for funding agencies and our investors. Well, these are all the bad things about supervised learning. So no pain, no gain. Well, in the next couple of minutes, I'd like to shift gears and say, hey, supervised learning is great. It can help us understand some of these functions that were opaque to us and closed in terms of opportunities. But can I actually use physics to mitigate all of these disadvantages of supervised learning? Can physics help mitigate these limitations and drive learning as a physical regularizer? Physics-inspired learning. So just the opposite of supervised learning that I just told you about virtual staining. Now, to answer this question, I'll tell you the story of Gedankennet. So, well, German is not as popular as in Zurich here. However, I'm sure you know what Gedanken means. How many of you do not know what Gedanken means? Okay, yeah. Gedanken means thought in German. It's popularized by Einstein through Gedanken experiments, thought experiments, general relativity, right? So here, we're going to use the same framework. Gedankennet is the story of an AI that is tasked with reconstructing holograms through thought experiments. That's where the name comes from. We want to do thought experiments. So the story goes like this. Imagine your favorite AI living in Jupiter without knowing anything about humans. So it doesn't have any experimental setup, no lasers, no samples. It doesn't know humans exist. And it doesn't know anything about our tissue samples or our samples, or how our faces look, anything. However, somehow it knows about physics and electromagnetics. It knows the wave equation. Well, waves propagate the same way everywhere based on the wave equation. The same in Jupiter, the same on Earth. So what this AI is going to do is, it's going to have Gedanken experiments based on the knowledge of the wave equation, Maxwell's equation. And without any experimental data, it's just going to hallucinate experiments and train itself about reconstructing holograms, giving us phase and amplitude of a sample based on an intensity holographic measurement, QPI, quantitative phase imaging. I want to solve that. Now, all Gedanken, no experimental data. Once you're ready, based on Maxwell's equation, we'll send the Gedankennet to Earth. First time I give you an experimental hologram of a sample that you've never seen before, I want it to be correctly reconstructed. Zero-shot learning, first time experimentally seen. So this is the framework of self-supervised learning through thought experiments based on physics consistency. Physics consistency is a very powerful framework if you know the physical laws, which means if I were to take, for example, this pointer and drop it to floor twice with the same initial condition, it will exactly follow itself because physics is repeatable, consistent. So Gedankennet thinks like this. It's going to look for only consistency of the physical laws, Maxwell's equations, wave equation. So since Gedankennet doesn't have any idea about human samples, it's going to hallucinate some garbage. These are randomly hallucinated objects without knowing what they are, just random pixels, where they will be treated as a wave, random wave of some kind, no resemblance to anything. Now, the first step here and the second step, these are repeatable experiments in a Gedanken format, which means very much like dropping the pointer to floor twice. In the first one, it's taking that complex field that is thought, hallucinated, and forward propagating it to a certain distance. That's the first repeated Gedanken experiment of wave propagation, just hallucinating it. Now, you form holograms here that these are the ones to be reconstructed, intensity only, you lost phase. Now, Pick up your favorite convolutional neural network or any function approximator that you can train. Differentiable, essentially, network here. We call this Gedankennet. Now, garbage in, garbage out. It's going to come up with some solution no matter what. It's going to give you an amplitude phase as a result of this inference process. Now, at this stage, the only thing that the Gedanken experiment framework is going to do is repeat the experiment again. Drop the pointer on the floor again. And that's where the second step refers to. And the only loss function that drives this learning is physics consistency. Repeated experiment must match the first experiment, so this loss function must be going to 0. Purely based on wave equations repeatability, by hallucinating examples with no resemblance, no experimental data, it's learning how to reconstruct holograms. Now, once it says I've converged without any optical hardware, no sample, no ground truth labels, no data acquisition, we say, hey, are you done? Yeah, we're done. Then we send it to Earth from Jupiter and give, for the first time, experimental data of holograms from real human patients. So here we're showing lung tissue sections, pap smear, salivary gland, prostate, etc. Gedankennet in the first shot can reconstruct the phase and amplitude beautifully well through physics consistency-based self-supervised learning that's data-free. Now, it's actually beating supervised learning. If you could have access to, for example, lung holograms with their ground truth and train a reconstruction engine, you would be overfitting to the data. You would be overfitting to the lung features, lung microscale features. You'll be overfitting to the experimental noise at that time, at that measurement, small distances and variations in those, which means supervised learning is failing with its external generalization from device to device, sample type to sample type. Physics consistency is universal because it's purely based on wave equation where it's always correct. In fact, this framework does not even hallucinate outside of the boundaries of wave equation, which means on purpose, we actually gave Gedankennet defocused holograms by different amounts. For optical microscopy, these are big amounts of defocus. Yes, it gave you a bad correlation with respect to the ground truth at the inference, but guess what? That they were not random perturbations on the ground truth. They were actually compatible with the Maxwell's equations, which means you could take its solution here of a defocused hologram and simply free space propagate it, it will give you a correct solution. That means it doesn't hallucinate. It's completely understanding the wave equation. If you give defocused holograms, it gives you the defocused complex field that is compatible with the wave equation. That's very powerful, which means you put boundaries on how it's giving its solutions through physics consistency. In fact, later on, we have shown that you can train for phase-only objects a Gedanken network that can do two things at the same time: holographic reconstruction of phase and amplitude and autofocusing, which means this network here, which we call Gedankennet phase, doesn't get any defocus as you give different holograms with different distances, axial distances. It learns two tasks at the same time. This was a good example where physics is helping learning. Physics consistency, self-supervised learning based on physical consistency was here guiding our learning. It's fast, cheap, just the opposite of supervised learning. But domain knowledge here is the physical understanding. So these are two extremes, from autofluorescence to bright field versus holography from the perspective of Maxwell's equations. In the last 5 minutes or so, I'd like to flip the coin. Here, physics was helping deep learning. Can we flip the coin and have, hey, can we have deep learning helping physics or optical engineering? The push-pull. Can we learn new optical design space, solution space from deep learning-based design? And here, I'll shift gears and talk about diffractive processing and finish off with this topic. This is just the opposite, where deep learning-based optimization is helping us to create new designs, imaging and computational camera designs. It's a framework It can be used for statistical inference, for computational imaging, or in general, an optical inverse design framework. The idea is shaping light-matter interaction within a solid body by dividing that volume into thin sections, where each one of these layers, you can think of it as a separate material or layer, where at half a wavelength, we are controlling the phase and or amplitude of the features. All of these features within that volume, there are trainable parameters. And deep learning here will be helping us for a given task to train this volume, which is one time done in a computer, but inference is all optical, which means once we're done with the training, the inference will be just happening through light matter interaction. So major advantage of this kind of a framework is this. It's computing through passive light matter interaction. Light that represents the analog information is already there. So the computation is done through passive light matter interaction as the object information is passing through these layers. The task is completed in a few tens of picoseconds. As these compact elements transmit light, you are done in your task computation. And it's scalable. You can fabricate these and compute in parallel. A lot of the examples that I'll share with you have been done using bigger wavelengths. So I'll pass this around. This is a diffractive processor that is composed of 3 layers. You can touch it. It gives you a topology that controls the phase information in 3 layers. And this is a computational camera system that I'll briefly talk about in the next 2 minutes. So that's why they look black to your eye, but those are transparent in terahertz waves. If you look at one of these designs, you will see some topology here. It's also on the surface of that system. If you touch the surface, you will see some roughness. That's encoding the phase information. This is another representation. There are 5 layers here. This random looking feature here is encoding phase at half a wavelength at terahertz waves, which is not an arbitrary topology. It's designed by deep learning. Can you hear me? My microphone is back or not? Yeah. So let me see if microphone is running out of battery. So it says low battery. So I guess you can hear me at the back. I'm not sure about Zoom, but sorry. So this is not an arbitrary topology. It's designed using deep learning for a given task. What does it do in this case? Well, it does classification of objects without digitizing them. Meaning that rather than capturing an image of your object that is unknown, here, as the analog information of the object is diffracting through these layers, it's routed to a detector that is pre-assigned to that class. It's not memorizing a few objects. This is generalizing to unseen data. So it generalizes what it means to be 5, 6, 107, etc. So it's all optical mode processing and classification of objects using basically light matter interaction. Advantages: low power, extremely rapid inference, tens of picoseconds, and scalable. So this system works experimentally if you can fabricate it. These are some experimental results with terahertz waves. Never seen objects before. It's not memorizing. For example, this is number 8. Most of the photons went here, which corresponds to detector 8. Yeah, there's some scattered light there, but maximum of those detectors gives you class scores. This is, for example, for other objects, the same idea, which gives you, for amplitude encoded objects, beautiful representation of how it's working. This system also works for more complicated objects. Here we're using phase encoding. Phase encoding is a nonlinear encoding strategy, which helps learning for these tasks. So for fashion products, it's the same idea. There are 10 different classes, and you want to not memorize these objects, but generalize to what it means to be a bag versus trouser, etc. These are experimentally showing you that by encoding the information at the input in the form of phase, you can have beautiful inference. For example, this is a bag, never seen before. Beautifully revealing its classification. Sometimes it's more difficult. For example, this one is a trouser. Well, there is some competition here, but it beautifully revealed it correctly. So these are classification accuracies, for example, for fashion M is something like 91, 92%. For MNIST, handwritten digits, you can have easily something like 98, 99%, approaching 99% with these ideas, especially phase encoding. To sum up, diffractive processor, analog computers. If the information is in the phase domain, amplitude domain, polarization, or spectrum, you can actually process them without digitizing. Especially important for computational imaging systems. We've been playing with this system for various different tasks, and I'll give you one application of it from the perspective of computational imaging. So let's use a diffractive processor to solve an inverse problem for us. Like, that's the part where deep learning is going to help us get some more physical insights about an inverse problem. Here, the goal is to do imaging through a random diffuser. Imagine there's an unknown object that is constantly changing, that is completely hidden behind a random phase diffuser. So you do not know the phase diffuser here and the object. If you don't do anything, you will be left with these speckled patterns that are constantly changing. Our goal here is to solve this inverse problem, where unknown objects change beyond your knowledge. Diffuser is dynamic. You don't know how it's changing. If you don't do anything, you have to live with these speckled patterns that need to be reconstructed, which you can do if you have a GPU-based model, let's say. But I want to do it in a few tens of picoseconds. As the light is reaching to me, I want it to be reconstructed, as shown here. It's analog reconstruction, all optical, a few tens of picoseconds, and no digital computing power, because light is already containing the power that I need. So if it's safe for you, you will be able to look at reconstruction with your eye. How does this work? To train something like this, you need to give thousands of examples of unknown objects with unknown random diffusers. They have a certain correlation length, let's say in this case 510 lambda. But every one of these are unique and they're randomly generated. By training the diffractive layers and the topology of the phase in each layer, we are penalizing the structural loss term at the output plane until these diffractive layers give you a decent reconstruction that matches what you put at the input, which means through these examples of random diffusers and random objects, we're learning the filters that we need to install in that 3D volume. You can think of this as a smart 3D filter that rejects the noise coming from random phase and passes the structural information of the object. It's a kind of like a matched filter in 3D. So in the rest of the slides, if you see B for a diffuser, these are blind diffusers, never seen before. After training is done, we show new objects never seen before through new diffusers never seen before. If the known diffusers, the K refers to known diffusers, which means these are some of the diffusers we used during the training. The difference between the known diffuser performance and the blind diffuser performance must be statistically insignificant. And that's the signature of a beautifully trained model. That's how this system is trained to reveal these kinds of reconstructions. This system actually generalizes to be a beautiful imaging system that works for samples that were never seen before or types of samples that were never seen before. In fact, gradings are for the first time shown. It was trained with handwritten digits, nothing like a grading. For the first time, with new random diffusers, we're showing gradings, and it's actually doing a beautiful imaging performance. Yes, there's some noise, as you can see here, but it's quantitatively tracking the period and filtering out the garbage from these unknown diffusers. So it generalizes to be a general purpose imaging system resilient to unknown phase perturbations along the optical path length. We tested this with a terahertz system. These are the diffractive layers that we converged, that we fabricated. It looks like this. It's 3D fabricated. You only see the first layer. The other three are into the board. I'll tell you what I'm learning out of these 4 layers. In the next couple of slides, I'll tell you what physical insights you can get from these layers. It's not random. It's beautiful in terms of how it works. These are some experimental results showing you that it actually works experimentally. And this system actually does not overfit to the presence of the diffuser. For the first time, if you take out the diffuser, it gives you an even better reconstruction. If you change the diffuser's correlation length, so this is a new diffuser, never seen before, but half the correlation length, the finer gratings of the phase, it even then works with a compromise. So this tells you that it's actually physically beautifully well. It's not overfitting to the presence of the diffuser. It works as a general purpose filter. To understand how physically it's working and what kinds of inspiration you can get out of this, we got to look into a design of a diffractive processor without any diffusers in place. If you take out the diffuser and train from scratch, this is the phase pattern that you get from the first layer to the last. If you zoom in, you'll be seeing that the network, actually deep learning, is converging to a micro lens array. Those diffractive planes are converging to a self-aligned micro lens array, where each one of these phase islands is a densely packed array of lenses, which are, if you take the first layer, shoot array, they're self-aligned. That's how it's making up for diffraction. Now, if you put diffusers along the optical path lane, what happens is this. You retain the backbone of the micro lenses. You can still see the micro lenses, but they're opening up in space, where there is a random looking phase pattern surrounding those micro lenses. In fact, if you look at those micro lenses, they're also self-aligned, which means from the first layer to the last layer, the positions of the micro lenses are by and large aligned axially. But depending on the difficulty of the problem and the correlation length of the phase diffuser, they open up some space. That space is for your filter. That's an optimized phase filter in volume that takes the modes of the random phase diffuser and scatters them out to clean up your imaging backbone. This is my imaging backbone, but that's not sufficient. It needs that filter around them. That means if you just take the micro lens and isolate it, micro lens array, it doesn't work. It can do an imaging system itself, but with random diffusers, it gives you a spectral pattern. Only with the combination of the phase patterns that are optimized and the micro lens, it gives you a filter and an imaging system at the same time. This is kind of like the gist of learning. If you erase the code and replace it with another random pattern here, it also doesn't work. It's an optimized 3D volumetric filter. So this is basically the physical insight behind that system. I will stop here in the interest of time. How much time do I have?
5 minutes, but so I'm sure there's some questions too.
Okay, so everything that I've described to you is getting help from deep learning based optimization to create a physical system that is helping design better computational imaging systems and solving inverse problems. I guess equally exciting and arguably perhaps even more exciting is the collaboration between digital AI and diffractive networks, which means you can actually have best of both worlds. Part of the computing is done in the analog domain and part of it is done in the digital domain. And they talk to each other and optimize for each other's performance. A good example of that is actually learning diffractive optical communication through opaque occlusions, around opaque occlusions. So think of a problem where between me and you, there is an opaque occlusion. And there's no wall, we're in free space. I want to send information to you, but occlusion is so big that I cannot send a direct ray to you because it's just blocked. What we've learned is that with diffractive decoding, you can shape up with an electronic network your message so that it uses the edge scattering of an occlusion to communicate with the diffractive decoder to give you the output message, which means this is spherical wave engineering. Any opaque occlusion, whatever topology you have, square, rectangle, whatever, it has an edge discontinuity. That edge discontinuity is composed of spherical waves that I can program. And that's a great collaboration between digital AI shaping your messages into spherical wave engineering through the occlusion edges to decode the information at the output. So we've done this experimentally. I'll finish up with a movie to show you how it's working. Basically, this takes a digital encoder network that takes any arbitrary message, infinitely many, and creates unique phase encoding at the input aperture. The occlusion is dynamic and it's opaque. And its topology is not known, it's arbitrarily changing. So this digital encoder and the diffractive decoder here are jointly trained to understand the spherical wave encoding coming from this plane to the edges so that you can actually decode the message. If there's no smart engineering here, this is your aperture. You see nothing because opaque occlusion is blocking it entirely. Through the decoding of the diffractive layers, the spherical waves coming from the edges can be actually forming your constructive interference at the desired message of interest. This also works for bigger apertures. Here, for example, the lens would see nothing. This is bigger. You've lost your numerical aperture, so to speak. As a result, the reconstructions are worse, but still they're stable. As the occlusion is dynamically changing, you get a beautiful reconstruction. So to sum up, I think we're having a fascinating time playing as a field with diffractive processors and deep learning ideas, kind of the push-pull between the two fields, optics, photonics in general, and deep learning and optimization. Sometimes it's one way where deep learning is helping physical understanding of designing systems, and sometimes actually the other way around, physics helping deep learning to get better. With this, I'd like to conclude, and thank you very much for having me, and thanks for